All right, so it is 9 a.m. Pacific time, our scheduled meeting time. So I am going to go ahead and begin to introduce our speaker today while others join. So welcome to our AI Institute seminar series, and thank you all for joining. Today we have a guest speaker named Oriol Lehmkuhl, who is a senior researcher at the Department of Computer Applications in Science and Engineering of the Barcelona Supercomputing Center. He leads the large-scale computational fluid dynamics group, and he also holds a PhD in mechanical engineering in the area of computational fluid dynamics at the Technical University of Catalonia in Barcelona. His main research interests are related to turbulence modeling, multi-phase flows, high-performance computing, and multi-physics and multi-scale modeling, with a focus in applications in aerodynamics and biomechanical applications. Today, he's going to be giving a lovely talk on the integration of CFD with data-driven and machine learning methods. And without further ado, I'll allow Oriol to begin his presentation. Go ahead.
Thank you. Thank you for the invitation. And let me share the screen and put this small, because if not after, I will see that. So I will talk a little bit what we are doing in my group, no? And trying to take advantage of machine learning, okay? But integrating with our traditional CFD strategies, right? So first, I want to explain a little bit my view on supercomputing, no? Because all of this is linked of how CFD it's interfacing with HPC and how we take advantage of that, no? So my particular view is that I was in Terrassa 20 years ago, at the beginning of my PhD, and there was a group of professors that they will do this type of machines, no? These are called BOB clusters, right? And at one moment we were having the biggest one of Spain. But these were normal computers just with a normal network altogether. And we needed to do calculations here, no, in order to be competitive. And well, I developed my code with the rest of the people of the group, right? And we begin to do this type of simulations. Now, low Reynolds, it's turbulent, but it's low Reynolds from an industrial point of view, but already unstructured type of meshes, right? But this was very long. Actually, this calculation, the one of the cylinder, it's like 6 months, no? In a machine like this. And then suddenly in my country, they did build the first Mare Nostrum. And it was a machine with 2000 CPUs, no? And we were one of the only groups doing CFD in Spain that we were able to take advantage of that. So we did get access to the machine and we did begin to put more complex geometries. So instead of a cylinder, we were able to go to NACA's profile, right? We were able to increase the Reynolds a little bit. And well, it was like a huge step, no? Going from a cluster that we were maybe having at most 64 cores to play with it, right? To have 2000 or more, even in Mare Nostrum 2, it was like 4000, I believe. Okay. Then the time was evolving and we get the other generation of Mare Nostrum 3 and we were able to continue on these simple geometries, no? But we were ramping up the Reynolds, no? Now we were able to go up to Reynolds almost 4 million. You can see here some of the images. And of course, these calculations were very costly. So as well, months, no? Of calculations on thousands of cores because now the machine was able to have tens of thousands of cores, no? And we were able at least to look for very complex Reynolds number already in a very simple geometry. And with the other generations of clusters that they were arriving, right, we were able to put more in, relevant configurations. Like this is as well high Reynolds, but with different roughness. And then we were able to understand how the roughness was changing the boundary layers in those plus bodies, etc. Right? But if you notice, this advance that first was very fast and after was more, well, a little bit of more complex geometry to increase a little bit more the Reynolds is where we are, etc., was stalling a little bit, right? And it was stalling because at one moment, instead of having this straight line, no, that we were having, we begin to have something that is dropping, no? And it means that we were not following anymore the Moore's law, no? And although the increase is massive, no? Because this graph I like a lot because what you have in the middle is the biggest supercomputer of that particular year, right? This is to add all the top 500. So it's the power of the all top 500 together, right? And this is the last of the top 500. And you can see that an iPad 4 is as powerful as the biggest machine in the world in the 94. So we have huge boost on performance. No, another number that I like to say is that a graphic card that a teenager may be having right now in to play, no, in his computer, video games, it's as powerful as the first Mare Nostrum, no? So we are always growing, but now the growing is stalling. And it's stalling because of the clocks of the CPUs, right? You will understand where I go at one moment. And this stalling comes from when I was beginning the PhD actually, and it has been stalling quite a stall, no? So the solution from the computer science engineers, no, that they were doing the hardware, is to begin to put more cores, no? So because we are stalling the frequency, we stall the frequency because we are stalling the power that we can put on a core, no, because of thermal problems. So what we put is to put more cores in the dice, no? And then we begin to have more and more transistors. And with it, we were improving, no? And we were maintaining this this part, no, almost straight until now that is not straight anymore, no. We were maintaining because we were able to put more and more cores inside the dice. But now the problem is that the cores are so small that we are at the limit of what we can manufacture almost, and we are at the limit that a particular electron will interact with the other electron, no, of the core, and then you cannot have a byte, no. So the solution is to put a lot of cores, but not more small cores. And the best way to put a lot of cores very efficiently are the GPUs. So if you look the trend, most of the biggest supercomputer clusters have been adapted to GPUs because it was the only way of sustainable of maintaining this paradigm, no? Of having a lot of cores, maintaining a little bit the power that you can use per core in order that everything is efficient but is reasonable. And particularly, all those GPU systems were very efficient to do product matrix multiplications, no? And you can see this trend if you look from this video point of view, no? So this is what I was explaining, the typical performance before my PhD, the drop that we are observing. And then since GPU has been optimized and NVIDIA has been, I say NVIDIA because it has been the main player, no? AMD has been always late from the scientific point of view. They have begun to really improve the tools, no, that we have in order to code inside the GPUs. We have recovered the old curve. Okay, this has enabled a change of the things that you can do because GPUs are very efficient in order because of their design, no, to do certain matrix vector and vector type of calculations. Okay, so you cannot do anything following this performance, no, unfortunately. You can do some things following this performance and continue the loose mode, no? And this has generated a paradigm shift in how we do calculations in general, no? And how we do our scientific work. Because this huge performance that GPUs are giving us has a direct implication on the exposure and how machine learning has evolved so much in these particular years as well. okay? Because they are very efficient for the type of calculations that machine learning has. So until before my PhD, no, and it was as well my PhD, no, we were having these three pillars, no. We were having a pillar that is experiment, another that it's people that imagine laws, no, and follow mathematics and follow as well intuition, etc. They formulate laws, no, that after with experiments and in our last century and now in our century using computers, no, we can see if they make sense and we follow the reality or not, no. And thanks to these new big supercomputers based on GPUs, where the machine learning type of architectures they can be trained so efficiently, now we have another paradigm that is to use this data in order to generate those data-driven models, no? That they don't are on these two categories, no? We can hybridize, and I will talk about how to hybridize, no? But it's another, let's say, pillar that is interacting with these four pillars. So the question is, and is what I'm going to talk, is how we are adapting, no? From going to here, that is my background, no? Normal calculations with normal clusters like I was showing, to take advantage on that, because now the supercomputers are building for this pillar, not for this pillar anymore, in order to continue contributing on fluid mechanics and on um, engineering. Okay, you will see which type of industries we are working with. So this is not just my work, it's the work of my team. The team is big now. We have about 27 researchers. If you put the master students and the PhD students and the researchers that are on the team. We focus on very big type of computational fluid dynamics problems where the only way to address those problems is to use supercomputers, right? And we have active projects on these four areas, okay? On urban flows, you can see here a scale resolving calculation of the neighborhood of the University of Barcelona. Actually, in the middle is the BSc facility. We work on wind energy, on resource assessment with different companies and as well on European projects. We work on aeronautics with companies like Airbus and ITP Aero. And as well, we work on different European projects from more applied to very fundamental for aeronautics. I have been granted with an ERC, Synergy ERC with the University of Purdue and University of Madrid, Polytechnic of Madrid, for aeronautic applications. And we work as well on external aerodynamics for that. Now we have been working in the past a lot with SEAT, and now I believe this year as well we will be working with them. Okay, so the first thing is that you can see that all our calculations are transient, so we did need to change all our software in order to be able to exploit these GPU clusters, no? To do that, we have an in-house code that is open source. You can check if you're interested. It's based on spectral elements and structured spectral elements. We can do big calculations of full aircrafts. I will show after an example. This is, for instance, for an aircraft of Airbus Defense and Space, no? That is the guys that we are collaborating with. And thanks to the GPUs, we can do these big calculations using well-modeled LES. It depends on the angle of attack, but those calculations could be between 12 to 48 hours. And usually using meshes about 200 millions to 500 millions. And if the geometry is more complex, you could go to 1 billion or so. Okay. And this allows us to generate a lot of data. And is one of the concerns that we have. Here you can see the scalability of our code, no? Running the NASA CRN high leaf problem with a mesh of 5 billions. And you can see that we can scale very well up to 2000 GPUs. This is half of Mare Nostrum, so it's a lot of GPUs together. And you can imagine that I believe that just the measure of this case is 1 TB. So big, a lot of data that we can generate very fast. I put here some examples in order that you can see that with this type of calculations for very canonical geometries like the NASA ham. This is a case with a Reynolds of 1 million, and we are using 2 billion points. We can really follow very well experiments. I put here another calculation from the group of Malik, and you can see that they were using 900 million control volumes. We are using 2 billion, and we are closer to the experiments. We are actually, if you look, this is the flow. You can see it looks very nice. Of course, it's 2 billion of the degrees of freedom, and you can see more interesting the skin friction really follows very well the experiments. We see the laminarization, we see as well the same size of the bubble and the pressure. So it enables to do these kind of calculations. These were run by one of my PhD students in less than 1 week and using the debug queue of Mare Nostrum. So right now it's a cheap calculation, and some years ago it was an almost impossible calculation. And this goes as well for the real industry applications. This is one of the aircrafts of Airbus. As I was explaining, we use spectral elements. We usually begin with a low order. It's not low, but the AP2 type of simulation, and then we interpolate up to P4. And the results that we get usually is in P4, and then it means that the message goes from 100 million to 1.5 billion degrees of freedom. Okay. And you can see here, I can show just the colorful pre-dynamic type of pictures. I cannot show the results. I will show the results now of the CRM high leaf, no? Just that you can see that we can then generate maybe these cases. They could generate a lot of data, but usually we are just interested on the drag, on the pressure distribution, maybe the shear stresses at the skin of the wings, etc. Okay, so we are not generating that many data, but it's useful for the industry because it's the real geometry and we are quite predictive. No, here you can see for the NASA CRM leaf an angle of attack that is not very big. I believe, yeah, it does not work. It just seems the angle of attack, but I can compare them with the runs of Airbus, and I can trust the runs of Airbus at this angle of attack. And you can see that with ball model LES, we can have very close results for the leaf and the drag, and as well with experiment. So here, then we have two things, no? We have the capability of doing industrial-like simulations, no? Quite fast. And we have the capability of doing more type of research and more focused, like almost DNS type of calculations or more simple cases where we generate a lot of data. And I will talk how we are trying to address these two problems, no? So we have now the capability of trying to do some optimizations, no? Using this type of very fast calculations and using GPUs and one model LES, no? That we can do of relative complex geometries. And or we could try to instead of doing that, no? Going to very big calculations and try to use machine learning to try to alleviate the amount of data that we are generating, no? And try to make more easy to use this data for the users of our software, no? And applications. So first, I will talk about the optimization problem. I will talk of the work that we are doing on reinforced learning. For flow control, we are as well doing reinforced learning for geometry optimization, but it's less mature, so I prefer to just show that. This is a very collaborative effort. It is not just my group. We are working as well with Delft University, with the University of Michigan, and with the Polytechnic University of Catalonia. I put here the main names, no? And this is our vision. We would like one day that you have an aircraft, right? Where we have different active flow control type of surfaces. Here we are thinking on the just to use zero mass type of actuators, but it could be other actuators. It could be mechanical actuators where we are just changing the parts of we are doing morphing, no, of the wing. Could be more things. But imagine that we can have this, we can put all the synthetic actuators, we are able to run the real full aircraft, we are able to train a reinforced learning type of algorithm, okay, where we did all the simulations, we did put the virtual sensors, we did train the flow control algorithm in different flow conditions with this is huge farmer, no? Maybe I need all the Mare Nostrum 5 for the Julie machine that it's going to be the first exascale machine in Europe, just to my problem. So at the moment, this is not going to happen, no? You do this training, then you transfer the training to the real aircraft, and there is a very brave pilot that does some tests with that, and they retrain everything on real flow conditions, and then you transfer this to production. No, this may be silly, maybe it happens, but it's the vision that we have. And this is just a video of a very well resolved, it's not the full aircraft, it's just a section of the aircraft where you can see the concept of what right now we are studying. That is to put some synthetic jets, no? That they avoid to have a stall in particular flow conditions. That's a little bit the idea. So this is very difficult. So we have begin with a more simple case. We recently have published this on Nature Communication. And the idea is to put a flat plate with an incoming turbulent boundary layer where we tuning the velocities that we have on the top part of the domain, we generate a separation, no? A turbulent separation that remains stable. And then we try to put here the actuators, and with reinforced learning, we see if we are able to actuate that, no? And if you look in this paper, we were able to do that. I will explain more how we do this computational. You can check the paper because physically after it's not that much interesting. It's more that we were able to do it possible. And then I will show the next iteration of that is going to an airfoil and how on the airfoil this we are achieving this. Okay, so here the computational exercise is quite complex, no? Because we need to do farming on our supercomputer. We will have several GPUs that they work together to solve one of the problems, one of the possible solutions of the optimization problem, no? And then but they will not let us use all the computers, so we need to orchestrate of everything, no? So imagine I do a reservation for 100 GPUs, then I decide that I will do 10 cases, and for each of the cases I will use 10 GPUs, and we need to have something that it's looking for the resources, is sending the cases. When the cases are over, look for the results. And when you have enough results, you go to the reinforced learning algorithm, no? You calculate the new parameters and you propose a set of new cases that you should do. Okay? And we did this using the Smart Redis library. Smart Redis is a library developed by Hewlett Packard that allow us to have like a database between different applications and as well allows us to do this orchestration of the resources. Okay. And then we did a layer of Python. All of this is open, so if you look the paper, you can see all the different libraries and you can use it. And the main idea is that we have our flow, then we have some sensors, we have data from the sensors, we have data as well from some integral values that we calculate. We give this data to an agent that is just a network with a particular policy. And then this agent will decide the next set of cases that we should do. Okay? And you can see here for this particular case, a case that is not actuated and a case that is actuated. And you will see that the case here, it begins to be actuated with a reinforced learning agent. And there is one moment that you don't have separation anymore. Okay? So this was our first experiment. And we did try to go to a more complex case. Okay, this is done with our collaborators on UPC. And then we did decide to use an airfoil with a relative low Reynolds. Okay, it's just 60,000 in an angle of attack that you have stalled. We did put some sensors and look that at this moment, this is totally and practical, right? We are just learning how to do this research because one of the things that we are giving to the optimization algorithm is a set of points that are on the volume, no? So you will not have this on a real aircraft, right? So the day that we are very confident on that, we will begin to find ways in order to, from what happens to the surface, understand what happens on the volume, no? At the moment, we are trying to don't have this problem, and we use what we have on the volume, and we use what we have on the surface. And then we do as well this trick where we have some environments that are working on one part of the domain, others on this part, on this part, okay? In order to have more data that it's coming to the optimization algorithm and to take advantage that we at the end this direction is periodic and there are different realization of the same problem. Okay. One of the big problems that we have discovered is that okay, reinforced learning can work very well, but the reward that you put on your optimization algorithm is not general. So the reward that we were using in this case, okay, is not the same reward that we need to use on this case. And this is not the same reward that we use when we do a cylinder. You will see that we have as well quite a lot of cases, okay, playing with cylinders. And at the moment, I will show results that are very nice, and you will see that here we were doing a reward where we were combining some unactuated, the basis unactuated drag and leave, some time averaging that we were getting from the leaf and drag with some non-trivial combinations, okay? And thanks to that, you will see that we can have better solutions. It's better, this one. This is the leaf for the baseline, so it's on a stall. You can see a classical type of control is the red. You can see the reinforced learning discovery, okay? And it's better. And it's way better when you look the drag. The drag, you will see that with the drag, it's way better. And it's way better because we select less. The typical flow control strategy is to find a function that it's an harmonic function, so it follows some sinusoidal type of function, and this gives some fluctuations on the drag, right? That you don't want. And the reinforced learning finds a function that it's more pushy if you want, is following more all the fluctuations of the flow and don't allow these big fluctuations to develop. But I need to tell you that we spent some months in order to find this type of reward that was working well for here, okay? So yeah, one part of the optimization exercise is to understand which is the reward function that you have, and I'm not sure there is a general one for all the typical aerodynamic problems, for instance. A good thing that we discovered is that you can train on the coarse mesh, and then you can evaluate on a fine mesh. So we were training with 60 million, and we were able then to do a lot of training. You need hundreds of realizations, no, of the environment in order to be able to let the algorithm really to learn. But then we were able to evaluate that the algorithm was working on a fine mesh. He was using 400 millions, and everything was working very nice. Okay, this is a little bit the deltas that you can see. So we are doing better than the control, the classical control. And even if we put our parameters, no, in the classical in control, this is the DLR basic, is not ever as good because you need a different function. It's not that you can tune the sinusoidal type typical function and that's it. Visually, this is how it looks. So this is the baseline. You can see all the flow is full stalled. This is for the fine meshes. This is the classical, and you can see that yes, the lift may be better, but the drag is worse because you have all these transient things happening on top of your wing, no? So maybe it's not what you want. And this is what the reinforced learning is achieving. And you can see it looks like just the turbulent low angle of attack of this profile. Okay, so it looks very nice and it's very promising because it seems that it finds a way to really have in a higher angle of attack a behavior that is very similar to the lower angle of attack, but of course you have more lift because the angle is bigger, no? And this one getting some parameters from the solution of the reinforced learning. And you can see it's better, right? But it's not as good as this one. So this is one of the things that we are doing, no? And I believe there is a lot of potential. We are using this as well for mesh optimization, and we are beginning to have good experience. Okay, but I will say that although I'm sure that we will do this more and more, and with bigger and bigger machines is a very natural transition, and after as well to hybridize with experiments is the next step. Now we are in talk with experimental groups in order to see if then the training algorithm that we have could be useful in their experimental setups, and then we will ramp up to real world applications, right? I'm afraid as well that there is a lot of science that we need to do in order to better find and faster find the reward functions and the hyperparameters that we need for the reinforced learning. Okay? But the computational exercise is there and the tools that we have developed are open. So if you are interested, it's something that, yeah, you could explore. Okay. And the other thing is how we can use all this big data that we are generating, either to have some models that after engineers they could use, no? Or to reduce the amount of data that we are generating because it's not sustainable, no? We need to be able to compress this data in order that people take advantage of these big simulations that we are doing, no? As well, this is a multidisciplinary, inter-institutional type of collaboration. And you can see we are working pretty much on this stuff with NVIDIA, BSC, and UPC. And all the time I'm going to be using this for benchmark. Okay, it's the airfoil that you already have seen, one of the meshes that we were having of 50 million. A simplified car, the Windsor, with 100 million points of view. The Barcelona district of the university, and an aircraft. And you can see we go more or less from something that is small and you could run on a GPU to something that it's going to generate huge data sets because it's already billion of points. Okay? And we are interested on that, to generate drones that maybe could be integrated on optimization loops, or they could be used to generate synthetic data for engineering purposes, or to compensate, compress these big simulations and then have a way to really let people interact with these big data sets in a sensible way, no? Without the need to go to the actual supercomputer, to connect to the supercomputer and use the supercomputer in order to be able to do something with this data. So I will not talk a lot about the part of the surrogates itself, but I will tell you that there are two ways, no? One way is to go full machine learning route, and I will show that this is something we are doing. If you're interested, you can look this recent paper of Rakesh Halder from IT, where we develop a ROM that is based on autoencoders, but using a Kumpa variational autoencoder that it's a little bit different of the autoencoders that people is using. And it's nicer from our point of view because it may be not as accurate to reproduce all the scales, but it smooth well the small scales and you get just the big scales of the flow. And then it's easier to train a temporal network, an LSTM type of network, in order to have a complete room that could, generate synthetic data from that particular type of geometry that you have trained. And you can see here for a simplified car, this is just the symmetric part of the Windsor car. And after training, we put a point in the middle and we see how it's evolving, no? And you can see that with this type of autoencoder that Rakesh has developed, for new time realizations that are not on the data set, it's totally new time realizations, we are able to follow quite similarly to the actual real data. And when you use the typical autoencoders beta type that people are using for turbulence modeling, you don't follow it at all. And this is because it's very hard to really train the LSTM network because there is too randomness on the original signal that you are trying to train. So there are too many small scales, and this confuse the transient algorithm. So there is a lot of potential, but the basic problem is that if you go directly using the autoencoder or any CNN or GNN type of approach, if you use a CNN, and here we were using type of CNNs, you need to interpolate, no? Because they were thought for images. So first you need to interpolate, and you could lose precision, and if you go to 3D, then begins to be very inefficient, no? Because you need to interpolate to a uniform mesh. But if we do an aircraft, then you need to decide what resolution you want your network, no? You want your resolution at the resolution of the structures that you have on the flap or on the slant, or you want resolution at the structures that you have at the nacelle, that it's totally different, or at another part of the wing, no? So it's very, very expensive, and it's not trivial to do this decision. You could use graph networks, but as far as we know, and we are using graph networks more using RANS type of models, and I will not talk on that. It's one of the things that Raquel right now is working. But as far as we know, they have a lot of memory restrictions. So if we go to a big graph network, it's very fast. You lose, you don't have enough memory. So if we go to a mesh of 1 billion or so, we will need then to begin to think on divide the domain on different graphs and then look for the continuity of the graphs, etc. I believe that could be a route, okay, but more development is needed, actually. So we are more interested on hybridizing. So we are interested on hybridizing typical SVD type of building ROMs, no? POD, for instance, with the lending techniques. And this is what I would like to talk, no? And the first thing is why you are interested in that. Because all these type of algorithms at the end, we can turn it out in a SVD type of problem, and we can parallelize this very well. And then we will have, several time realizations of the snatch of our domain, and we will have then very big matrices where here is the number of points. So if I have 1 billion points, here it's 1 billion points. And if we have then 10,000 time steps, it's 10,000 time steps, it's a very big mesh, right? But we can distribute this on several ranks. We are not interpolating. These are the real points of my experiment or my numerical simulation. And we have been working in this last years in my group on different ways to do the very efficient disparallelization, right? This is not new, but the idea is that when you have the SVD, you can convert the SVD in a QR problem, where at the end, you have a couple of matrices that you need to deal with, and you need to do this type of R and UR type of decomposition, okay, in order to have your final system. And pretty much there is a version of a QR parallel decomposition. It was not done by us. Here is the reference. And we have put this algorithm inside our open source library, Pylon. It's a Python-based, very efficient type of library where we have developed, we have put all these algorithms in a very performant way, no? And here I can show you some examples for our database. So with these meshes that they were going from 50 million to 1 billion, you can see here the symbols, and then depending on the number of snapshots, of course, using a lot of CPUs, you can see that you could do this composition SVD, you can do your POD analysis in time of seconds, okay? So this enables us then to be able to build these big ROM models in supercomputers. You run the cases after, or in the meantime that you are running the case, I will discuss this. You can build your reduced model, right? And it's an output of your simulation. Luckily, you can do exactly the same on GPUs. And here I'm showing an example of our implementation on GPUs and a little bit just to know the numbers using just 100 GPUs of these are NVIDIA H100s with this measure of 1 billion and having 1000 snapshots, you could do your analysis in 20 seconds. You can see here how is our speed up. We follow what we should follow. And this is for, we have 4 GPUs per node. These are the number of nodes, so up to 100 GPUs. This is the weak speed up, is as well quite good. Of course, it depends on the algorithm. Some algorithms will have more bottlenecks, more serial part or not, no? This is already available, so guys, if you are interested, you could use, and then you can do really POD, SPOD, and other type of DMD and variations very easily using our tool. What is important is that in your core, you have an SVD type of problem, no? If not, you could not take. And GPUs are very, very nice, so you can have this type of if you compare just you are using usually one core to do this type of analysis, so you could go like 80 times faster using the GPU version. However, turbulence is very tricky. It's very tricky because, as you know, we have this range of a lot of energy where the energy is decaying, no? If you remember the spectra, typical spectra that you can read on the textbooks, no? On Pop and company books. And this decay of energy, it's for a lot of modes. So in the world of the SVD or POD type of analysis, it means that we have a lot of modes that they have more or less the same energy and they are all very important. So to be able to process um, 1000 modes, it's good, but maybe it's not enough and we need to process more modes. So we need to see a way where we can process a lot of modes, but after we can compress it in order to have a model that people could use. Okay, this is just the size of the database in order per snapshot, no, all the snapshots, in order that you understand a little bit the problems. So to do that, we use as well Smart Redis and Smart Sim. Okay, uh, it's very similar to the approach of the machine learning. We use Smart Redis to have a database in the middle where we are running our case, but now instead of passing some profs, what we are passing is the snapshots that we want that Pylon process in the meantime that we are doing the simulation. Okay, so the idea is the same. Now the GPUs are doing the big calculations, the aircrafts, and it's several time steps putting our data on the Smart Redis part, and then on the CPUs, Pylon is doing the SVD compression. Okay? To do that, there are some caveats because the partition that we use on the GPU is not the same partition that we do on the CPUs. So we need to do rebalance, we need to distribute a little bit the data, etc. This has been is explained on several papers, was part of the thesis of the net. It's something non-trivial, okay? Because if not, the CPUs are not taking full advantage. And this is very nice because usually in a node of Mare Nostrum, for instance, we have 4 GPUs, but we have 80, I believe. Now I forgot. 80 cores. So there is about 76 cores that are not doing anything, okay, per node. So the idea is that all those cores collaborative are helping us to do the composition. Okay, so we do the POD, but we want to compress more. And the first idea that we did have was on the QR algorithm, we have this matrix, the B matrix that we call it, no? Try to compress the rows, no, of the matrix, the columns, sorry, of the matrix. And we call it the Gabi algorithm. It's not related with the Barça player at all. And we have a paper, no, about it if you're interested. And the idea is that we do the normal decomposition, but before storing everything, we train the autoencoder, and at the end we have a smaller type of model that it's more easy to manage for the users. And it works very well. Look, we just need here the way to compress is to use an autoencoder, a very simple autoencoder. And then what you can see is that with just three latent vectors, we can recover all the energy that we were having with the field POD. So we go from needed to store these 1600 modes to just three latent vectors. So it's a huge improvement. We tested this as well for the Windsor car, for the middle plane. You can see here the recovered fluctuations for the pressure between the well-modeled LES and the Gabi algorithm. It's very good compression as well. And we tested on the Barcelona district. So one of these two images, one is the reality and the other is the Gabi algorithm. Hard to tell because even if you do, sorry, if you do a line that it's crossing like this, you will see this difference, no, for the fluctuations of the velocity. So it's not exactly perfect, but it's a very nice compression and it reduced already a little bit the data set. The only thing is that it's just this part, no? It's just this matrix, the one that we are compressing. The big matrix is the Q, no? So these last months, we have been thinking how we can compress the Q. We did some math, and compressing the Q, it means more or less a factor of 20 on the compression, no? So it means that if you have a database that it's 30 terabytes, you could go almost to 1.5 terabyte, which is a very nice reduction, okay? So we did spend this last summer working on different ways to do this compression. And well, the first thing that I want to stress as well, that thanks to the smart Redis, and we did it for the case that we were doing this type of compression of the queue, uh, people sometimes think that it's better to go through the file system. So here we were comparing the time to store a snapshot and the time to really communicate through smart Redis and putting the data on the database. And you can see that for all the cases that we tested, and we were testing quite a lot of GPUs combinations and meshes, no? It's always faster to go through the Smart Redis interface and just use the memory. So it's a very nice thing. And this is actually the algorithm working. We have two different architectures for the autoencoders. The good one is the architecture 2, that is the more bold line, dashed line. First, you can see this is actually the compressed snapshot. And, sorry. And at the end, we achieve a better compression. It's about 25. And we tested the fluctuations of the velocity. You can see are very good. But as well, we tested the budgets of the kinetic energy equation. And you can see that we follow very well the budgets. These are very good news. It was very surprising for us. And actually, the only term that it gets not well represented is the red one, that it's the dissipation. And of course, dissipation is very sensible. And it's something that we are not following well, no? But this is very nice because you could even use this reduced model in order to do some advanced statistics and to assess the flow, maybe put Lagrangian particles and use it for other type of analysis, etc., without the need of interfacing with the whole data set that it's a very expensive thing, no? You can see it's about 4 terabytes, no? The full data set. Okay, another alternative is to do the POD with not so many nodes instead of doing in Gabi, no, that we put a lot of modes and we compress the algebraic system, is to say, okay, I'm going to put not too many modes, I'm going to reconstruct, I'm going to see the different gap that I have on the energy. For instance, here you can see the energy, you can see in the reconstructed you can see the original, and then we have this gap, and I try to train a deep learning closure for this gap, okay? And this is the other exercise that we have done. We have done this exercise for two cases, for the middle of the Windsor car on the wake as well, and for our building using the the data that I showed before of the Barcelona simulations. Here the training is quite expensive because we will have a transformer for each of the point of the mesh, no? Because you do the POD, and then for each of the point of your mesh, you will add a transformer that it will put this energy that we have. So it's like a super type of resolution algorithm that complements the POD. Then this is very expensive because you will then you will need to train like 1 billion transformers. To reduce a little bit the complexity, we were just taking slices. But this algorithm is full unstructured, okay? So these were unstructured slices. And the transformer that we were using, it was developed by Marcial Sanchez from KTH. It's not our transformer. And the idea is that we take 48 time correlated snapshots, we look the error of the snapshots, and then we train the transformer with a particular easy attention mechanism that it's thought for fluid mechanics. You can see here a little bit how the transformer it's learning you can think this as the PDF, no, of the error and the energy, and you can see that when the tension gets bigger and bigger, each time we do better. But of course, there is one moment that we are if we test a case that it was not on the original data set, we don't do as well, no? So usually we like to have a size that it's about 128. And here you can see on the actual test case, no, the fluctuations of the velocity in the middle of the symmetry plane, and the wall model LES is the original one. This is the POD. This is what we get putting the transformer. As I was saying, the good 128 is the one that is not overfit. So this is for an angle of attack of the database that was not on the training. And you can see it improves a lot the POD, no? It's this one, the dashed green, no, the dotted green is the one of the 128. And we did put here a super resolution algorithm based on GANs that it's very typical just because to see that is actually better, no? What we are proposing works better than the traditional things that are used to enhance images, no? We believe that it's important that we put the physical part that we are putting on the POD side. And then we try as well on the city, on Barcelona, just the POD and the closure, putting the optimized parameters. And you can see that it's a very nice improvement of the world model LES. And that's it, no? I hope that it was interesting for you guys. So it's a little bit our vision of how HPC is allowing us to generate a lot of data and how we are beginning to take use of that, no? These two components that we can generate data very fast. So we could use machine learning to help us to optimize very complex systems, or we are generating a lot of data and we need to find ways to reduce this data in order that people can use this data for their problems, to understand the problems, etc. Or inside optimization loops, that is something that we are beginning to think as well. And I don't know if there are questions. I stopped share because I cannot see the questions, I believe.
Thank you so much for the amazing presentation. There are a few questions in the chat. And so I can read the questions out in the chat. And then after that, if people have questions, they can feel free to raise their hand and I can select them if they want to speak it out loud, or they can put it in the chat if they prefer for me to read it out loud. So one of the earlier questions by Marco was, how is SOD2D at handling boundary conditions and what method do you use?
Yeah. So 2D uses spectral elements, so we are body fitted, and it's one of the things, no? This is high order type of finite elements that are convenient because the shape functions are orthogonal, and then we can be very efficient. But we have the whole representation of the cat. Actually, it's a high order representation of the surfaces. Yeah.
Thank you. And Marco is also asking, does it support differentiability well? So if you have the gradients like dE over d theta directly, it could help augment the RL algorithm search during training. And I think this is related to when you were talking about RL for flow control.
Yeah, that's a great question. Super interesting. The thing is that at the moment, no. So to the does not have the actual Jacobians of all the equations. There is a team of in UPM that is working on that. And yeah, it will be very interesting when we have that because we could use directly this on the optimization algorithms. Yes, I do agree.
Thank you. If anybody online, oh, we have a question from Nick. About the RL method, is it using a Q network and policy network?
Yeah, we are using yeah, POP as a policy. Yeah.
Thank you. Sun is asking, could we use the computational center outside?
Well, what did you mean? To access to BSc facilities? I- If the question is that to access the BSc facilities, you need to have a PI. So it's all competitive. So you need to submit an application. There are EuroHPC applications where you can access and ask, but the PI needs to be European
Mhm. Okay.
on this application. Yeah.
Mike raised his hand, so Mike, if you want to unmute yourself and ask your question.
Sure. Thanks for your talk. I've been working with Satoshi Matsuoka at Niken regarding some surrogate modeling using GNNs. I know that the limitation of GNNs will be communication at hyperscale. And the latent space of the model is fairly small. So at inference, you're not really dealing with a lot of you're not doesn't cost a lot to actually run the model itself. It's more communicating the information across, your partitioned graph. I'm just curious how, if you've been working with the Mare Nostrum architecture regarding these uh, graph partitioning algorithms and some work you've been doing, because I know you said you've been working on this, some work
Yeah.
you've been doing to do graph partitioning.
Yeah, we have been working, and at the moment, we have not been very successful to improve what you are saying. Okay. Um, so at the moment, we are using graph network in relatively small problems, and when we were trying to go to very big problems, we were having problems on the parallelization side because of the communications, and it was not really very efficient. And now we are beginning another project, an European project, and there is a partner that is working with a particular algorithm that, yeah, we have the hope to test it on the machine and see if this is improved. Okay. But yeah, at the moment is the main problem that we have, and we don't have any particular solution for the graph networks. And it was one of the reasons that we moved to explore as well this hybridization of more traditional SVD type of algorithms with machine learning.
Thank you.
I actually had a question myself
Sure.
about the RL for flow control. You mentioned that choosing the reward function is very important. Was there ever a case where, depending on the reward function that you chose, you found that classical control worked better?
Yeah, many of them.
Hmm.
Yeah, yeah, yeah.
Okay.
So there is a problem that we are still trying to understand, and as well on the geometry. We have a senior researcher, Bedri, that it's working a lot on that. That is apparently the learning policies, they don't like things that begin to behave very stochastic. And then when you have a policy that is not very deterministic, they get confused very fast, and then you cannot really have a good rate of learning.
Mhm.
And yeah, and this can happen very easily, no, depending what you put, because we do transient problems and it's turbulent. So yeah.
Thank you. So we are at the hour. If there are no more questions, we can begin to wrap up.
Perfect.
Yeah.
Thank you, everybody. It
Thank you
was a
so much
pleasure.
for
Yeah.
joining us. It was a really interesting presentation.
Thank you. Bye bye.